So I'm going to talk a bit about zero knowledge on Polkadot right at the beginning, and then I'm going to tell you some of the stuff we've been working on at the foundation, and specifically sort of I'm going to explain something about how you should be doing, how one should be doing identity systems on blockchains and in general online. And hopefully I won't get too off into rants about what the Web3 consortium people are doing with identity stuff. Okay, so how to do zero knowledge in Substrate. So first of all, of course you can build Rust to WASM. This will work. That tends to be about 10x slower for really highly optimized code, which isn't so great. Okay, what did Ethereum do? So Ethereum, they added, adding one curve, which with pairings, they needed to add about 9 precompiles. Those are the equivalent of host calls for us. Okay, so because they're adding a bunch of these, each of these things adds some maintenance burden, some risk that something doesn't quite work the way people want to do it in the future, stuff like this. So this means they're going to be, in the end, they'll add fewer curves probably because of that, and also just because they're slow. And some of these precompiles, from our perspective, really aren't necessary. So like they have a precompiles for adding elliptic curve points, and we don't care because adding elliptic curve points is very, very fast. You can just do that in WASM. Also the hash to curve. Again, these things are very, very fast. You don't really need host calls for those things. But because of the way, when you start thinking about things as a scripting language, then you have to support this kind of stuff. Also, because they end up with, as I'll point out later, so Gross16 is sort of, when you look at the equation, it looks like 4 pairings. When the way you would actually implement it is with 3, because you just have a constant there, but they don't support that because, again, scripting language. And there's some other things that become problematic when you're sort of pinned down in how you work with the elliptic curve points. So, all right, so what are we doing? So the thing that we're doing, and I'll get to sort of something that maybe will stick out a bit more for devs in a minute, but so what we're doing is we're adding host calls only for the very slow parts. Generally, the way cryptography works is there's certain operations that run in a tight loop, and it's like, how do you multiply an elliptic curve point by a scalar? Well, you take powers of it, you square it a bunch, and you add some of those in based on which bits are set in the scalar you're multiplying it by. So that runs in a tight loop. That takes a long time. And so we add something for that. So for single and especially multi-scalar multiplications, we have host calls. And then for pairings, we need 2 more host calls. Well, we need those, and we need 2 more host calls. We need a multi-milliloop and a final exponentiation. And that will also make sense to have something for operations in the target group of the pairing. But anyway, so we're not going to have, in the end, we won't need very many host calls. Something like 4 for BLS 12381. And we end up with something that's much more flexible. And in particular, this is the slide I really wanted to show people. So we can actually even simplify it from this, but at the moment, all we really have to do is have it, when compiling for native code, we use the direct arcworks. We use the curve crates from arcworks directly, and then we just have some modified ones that plug in the host calls for these things. So it's exactly the same Rust code, and it will compile and work, and it will be doing host calls, and this will all be hidden. So we'll have to deploy these things for certain stuff that we're doing anyway. They're not currently live on Polkadot or Kusama, but this will happen. And you can see the repo where we have these forked host calls. So anyway, if somebody wants to start playing with zero knowledge stuff on Polkadot, the important takeaway is that you can start playing with on your own on your own substrate. You can compile in these extensions and then these host calls, and then use and then use these crates. Okay, So all right, that's one of the most important things I wanted to tell people here is just that in the end, it's actually going to be very user-friendly. You won't have to code up stuff twice. You won't have to have like your Rust or C prover and separately a verifier written in something like Solidity. You'll use all the existing Rust infrastructure and just change the curves when you want to deploy it in a parachain. Okay. Other stuff I wanted to tell you about. So I want to talk about these ring VRF things we've been working on. So first of all, what does the ring mean? So a ring signature, so there's sort of two things that people do. Well, there's more, but for a while there's been sort of two things that people, in the beginning, what people were doing with zero knowledge in blockchains was ring signatures. Ring signature just means you produce a signer that proves that the signer, whoever signed it, doesn't say who signed it, but it proves the signer is in some list. And in a blockchain case, for something like Zcash, that list is the entire history of the chain. But there are smaller ones like Monero, you have to choose which blocks you're dealing with. And there's some things like deniable key exchanges where you do it with a ring of like 3 people. So anyway, ring signatures, there's a bunch of different ring signatures. But in general, this is what they mean is you sign something and you hide who is the signer. Okay. And now, so we also, a thing that people probably have heard of is these verifiable random functions. We use these a lot in Polkadot. They're just a signature where the secret key has attached to it or defines some random function. And what by random means is that what you get out of it is going to be sort of unpredictable element. And it will be unpredictable if either the secret key was unknown or if the input was unknown. Okay. So a ring verifiable random function is just a ring signature that also proves the evaluation of whoever the actual signers of the random function corresponding to the actual signer's key. So what you find out from this is that one of the signers has signed it, and you're looking at an evaluation of their function, but you don't know whose function it is. There was a question in the back? No, I was stretching. Okay, maybe. All right. So a regular VRF. The regular EC VRF looks like this without the red parts. I'm not going to put too much math on slides, but there will be a little bit sometimes. A regular VRF looks like this without the red parts. And there's this thing, it's a very trivial modification of this thing. We're calling it the Peterson VRF. It just means that the public key is a Peterson commitment to a secret key instead of just being the secret key times the base point. Okay. What's nice about that means that you can keep the same secret key, and as you keep changing this blinding factor, you can have a VRF that you don't know who the public key is. You don't know what it is. It's some public key, but we can hold the secret key fixed. Okay. So this is just one component of the thing. This doesn't prove anything. It proves the evaluation of the pseudorandom function, but we now need to be able to have a way to get to this Peterson commitment. So for that, I'm going to talk about zero-knowledge continuations. So these snarks can be very expensive. In general, what's expensive about a snark is it depends on what kind of computation you're doing. Usually they're running in a slightly different computational model. But in general, accesses to storage are extremely expensive in snarks, partially because there's a lot of computation involved in doing that proof into a Merkle tree or whatever. So what we're going to do, so what a zero-knowledge continuation means is that we're going to do that access once, we'll produce that snark, and then we'll keep reusing the same snark over and over again. Of course, there's a problem. Okay. There's going to be a problem with that, which is that you want the snark to be re-randomized. You need to change things. So this is what Gross16 looks like. This term is a constant, and this x here is what we call the public input term. So there's a bunch of generators which are determined in the trusted setup, and the x will have the form of the public inputs to the snark times these generators. And the Groth16 that we're particularly going to be interested in, it seems like a really stupid one. It says, okay, here's some commitment to the ring. Do a Merkle proof that some public key is in it, and do a proof that this secret key corresponds to this public key, and then just reveal the secret key. So this seems like a very dumb snark. I'm just revealing the secret key. In general, okay, this is a ZK continuation, which I call specialized Groth16, or special G for short. It means we're going to have some inner Groth16 that leaks secrets, but then we're going to have modified its trusted setup. So what the trusted setup will be is we introduce some K and a related point to it, and then the K you can just add in as if it was another element of the trusted setup, and then group it with the stuff that you wanted to keep secret to make your Peterson commitment that we needed on the previous slide. And then, because this K is not really a piece of the Groth16, it's still a piece of the full trusted setup, but it's not a piece of the Groth16 trusted setup. So the black parts here is a re-randomization procedure for Groth16. I can take a Groth16 and then I can just change the randomizing elements in it. And now by using this form of the K here and this other form from the trusted setup over here, which means that it'll show up in this term, so they'll cancel out here. Then I can get a actually, I think I need a minus sign. But anyway, then I can get have my Groth16 verification equation still check out, and now I have new Peterson commitments coming out with no relationship. So the result of this is a ring VRF where I do the proof once, and then the marginal signer cost is 8G1 scalar multiplications and 2G2 scalar multiplications, which is just nothing. Like usually, that's like not even a full constraint in the orbits, about one, maybe one or something, maybe. Okay, so why do we care? Well, okay, so first, before we talk about this, there are going to be other notions of zero knowledge continuations. You could do some, KZG is a little bit like Groth16. We could do a zero knowledge continuation from KZG. In fact, there are usually Fiat Shamir things in the ZK openings of KZGs, but they're reasonably cheap, so you can just do them. So it's fine. So one of the things we could do is we can have, when you think about the way one of these Merkle trees in a blockchain work, usually you actually have this Merkle mountain range, and then you could put all of those roots in a KZG, and then just as you need to merge them, you do. And what this means is that the users don't necessarily have to they'll still have to redo their Groth16 sometimes, but it's only logged many times. So it's still extremely cheap. There's another kind of thing. I figured out a crazy way to do revocations, which somebody can talk about later, but essentially it's doing a cuckoo filter in a KZG, which this means that you could remove things from the chain without giving up, or from the list, without giving up this append-only quality, which is very nice from the MMR. Okay. So how do we want to use these things? So in general, there's okay, so now we'll sort of take a step back from the math a bit. I just like showing that. Okay, we want notions of identity that are sort of safe to use online. And what's really bad that like the distributed identity people or just DID people and other things are doing is they're wanting to put attributes in everything. So which means that to use an online identity system, if all so there's the user and there's the service or whatever that wants the user to identify themselves. Of course, if the service needs to know something about them, that's one thing. But a lot of times all that a service wants is that, I'm only giving away free plays, 10 free plays of my game to each person per day, or I'm only giving away a limited amount of something, or I'm just preventing spam, like it can be just a blog, or, responses in a blog or things like this. A lot of times all people want is rate limiting. And so probably I should have gone these in other. Okay, so here's a workflow, probably should have done these slides in the opposite order, but okay, here's a workflow that I think makes some kind of sense, so we have the users, they scan something like a government identity document, which shoves that into a zero knowledge proof so that none of that will be leaked on chain, or does something so that it doesn't get leaked on chain. And then this just registers the user some public key in a database, a parachain, whatever. And then the user uses this ring VRF to make proofs that they're in that chain, and the function and the key that they registered is the thing doing the evaluation of the VRF. Now, how does that work? How does that give us identity? So you imagine, let's just think about a Web2 identity system that would work this way. So the user agent, the browser, validates a TLS certificate and checks its CT logs and stuff, and then it just signs a message which is saying, okay, in some auxiliary way says this is the current session, and it's something to prevent replay attacks. And then it says, as the input to the VRF, it just uses the website's name. Now, the thing that will pop out of that pseudorandom function is some random number that's a combination of the user's secret key and site, and it's basically a hash of the user's secret key and site.com. And that means that's the user's name at site.com. And there can only be one of them. Now, there's so what happens if we want some sort of right to be forgotten here? So we can do something else. We can say, well, okay, they don't use site.com. They use site.com in the month, and they have to provide both the current month and the previous one. Now what happens, now the result of this is, if a user wants to be forgotten, they have to go away from site.com for a full calendar month. And then when they come back, this thing won't be linked. Otherwise, what the site will do is it will just keep making a link. So this was the same guy. Okay? So you can do a variety. So my point is these ring VRFs are actually relatively functional. There's a lot of things you can do with them. You can mutate the. You can, by changing this input string, you can provide a lot of. Gavin calls it a context, but I still call it the input. But anyway, by changing it, you can produce a lot of different behaviors that represent what you're doing. Okay, here's another interesting thing, which maybe will be slightly depressing. But okay, so we have a climate change problem. We have a resource usage problem. Where what can we do? So we're talking about a rate limiting system. So of course it makes sense to use if this makes sense to limit the number of usages people can do, number of interactions people can have on a blog. It also makes sense for limiting like real world resources. You can we had a mustard shortage in France, not last year but the year before. If the government comes along and wants to distribute and wants to create a ration card system, they can use this, and it's anonymous, which is much better than not having it be anonymous. Okay, and so anyway, I think I already mentioned free-to-play games, things like this. So anyway, this gives us a lot of there's a lot of different stuff we can do with it. One of the things that's kind of nice in this ration card case. So in general, when you have a certificate system, well, of course, everywhere in cryptography we use certificates and certificate chains, but we have a problem when we have sort of a centrally administered certificate system, is that at some point you get some bad certs issued, either because there's a spy agency that wants something in there, or because, or just in the COVID cases, just some doctor did something, whatever. So oftentimes, this is why a lot of times when you have certificates, people want some revocation path. But in general, there's a problem with fraudulent certificates. This is why, in the case for TLS, they developed this certificate transparency log system. Okay, now what you can. Oops, no. So in what we can do. The thing that I want to communicate here, which I don't really have a slide for, is that when you have so In the case of something like the CA system for TLS, the certificate transparency log system made sense. There's no analog of that for anonymous credentials, not that anybody knows, except you can use ring signatures instead of anonymized certificate chains, which is anonymized certificate chains are what most of the DID people and what the W3C is talking about. So they don't really have any they're not thinking about revocation paths. But once you have a ring signature, you can do something. In particular, you can just audit the database or the parachain or whatever it is in the first place. So if, in this ration card example, if France doesn't, if Germany doesn't trust that the French president isn't issuing more things, they can just they can just audit the database. All right. So the pressing thing that we were interested. So this is a beautiful sassafras tree. The thing that we were very interested in for these in Polkadot, aside from the identity stuff, is actually from block production. So sassafras is one of these sacred single leader election schemes. This means that it makes a block every fixed time increment, every fixed 6 seconds, but you don't know who the block producer is until they make their block. So it's sort of, and sassafras sort of works like block production by Cards Against Humanity. We make a bunch of these, we use a ring VRF, we make a bunch of tickets, and then we just sort them. And we throw away the ones where the thing is too small or too large, or, well, two in the middle actually is what we throw away. All right, so disadvantages. The reason we say it's only semi-anonymous is because the network layer on an anonymity system is weak, but the shuffle-based, like the usual scheme that people think about for SSLEs are these cryptographic shuffle things, and that's what Ethereum is talking about with Whisk, but these are similar to what's called a verifiable mixnet, and they're so slow that what Ethereum was doing in Whisk is actually weakening the anonymity below what we can do with sassafras. All right. So the advantages is that we get the randomness. Prowess isn't the best randomness, but it's something. We can prove things about it. It's vastly more efficient than the shuffle SSLEs, or more secure once you've weakened them. And one of the very nice things from our perspective is that block producers can prove their slot in advance, which means that they can do things like open a connection to collators and prove that they're going to be the guy in 12 seconds or whatever. And another cool thing that's a little bit further down the road is, we're already putting this into the sassafras tickets, is to have a key. We'll register an ED25519 key in the sassafras ticket, and this could be used to open a bunch of. So if a parachain is using sassafras, then you could have a bunch of. Each block producer on the parachain could open a Tor hidden service, and if you want a particular time, you just look up what the key will be for that and talk to that guy directly. Which is that's a pretty nifty feature, because that means you can do AMMs and other things where the users are just negotiating on that one upcoming collator and literally doing it interactively. And so then there's no mempool, which solves a bunch of problems. And in principle, there's some better MEV defenses that come out of it. Okay, so I'm going to stop, and maybe I didn't leave a lot of time for questions, but maybe if people have some questions.
You guys have any question here for him? We have about 1 minute for the question. All right.
Yeah.
Please, sir. We get a hot mic for you. Here.
Yeah. Hey. Just a quick question. With sassafras, do we have a dependency between the kind of amount of stake that validator has and amount of tickets that it produces? So the more stake, the more tickets.
We didn't design that in. Handan was working on some variant of that. We can discuss that later if you want. The problem is, the simple kind of ring VRFs that I was talking about wouldn't do it. You can of course do that with a slightly more general zero knowledge proof, but you need to prove, like, you would need to have your Gros-16 output the stake as one of these secret things and then do an inequality proof in the thing. It could be pretty efficient, but we weren't developing it.